Hi everybody. The topic of today's lecture is genetic algorithm. Today we are going to talk about the working of genetic algorithms. It's a bit of history, and I'm going to explain you with an example how we use for practical problem. We will see a very simple problem. We will apply this algorithm on a very simple problem, and we will see how this is going to progress. So genetic algorithm is, as the name suggests, it's based on genetic material. Okay, so this is based on biological evolution. So the algorithm is operates on genetic material called chromosomes. So conventionally we use chromosomes, the word chromosomes, but since there are other materials, so we take the abstraction of chromosomes. So it was developed in the 70s by a bit of detail, John Holland, Michigan University, and to understand the natural systems and to make artificial intelligence systems that maintain robustness of the natural systems. It's a very powerful algorithm. It provides efficient and effective techniques for optimization and is practically used in a lot of applications, especially in the areas of business, science, and engineering circles. Okay, so how we apply this algorithm? We start genetic algorithm. We have a set of chromosomes. We transform our problem. So remember, it's a searching algorithm. It's a local search algorithm. So in searching, we have states. We transform our states into chromosomes, and from those chromosomes, we make a population. The first step is to make a population of certain individuals. From the initial population, we do selection of parents. So selection is based on fitness of individuals. Okay, in the population we have states, and states have certain fitness. We will see how we calculate that fitness. So after we evaluate the individuals in the population, we do selection, and after we select certain parents, we do you can say the mating of the parents, and we generate children. Okay, so in the third step, the children are passed in the third step, where we apply the modifications, genetic modifications. So genetic modifications may include recombinations, we call them crossover, and mutations. And after these modifications, we do the evaluation. Evaluation is a very important step. So what we compute? We compute the fitness of individuals. Okay, so the chromosomes that we get, the modified chromosomes we get, we evaluate their fitness values, and we see if we have achieved the goal state or the state that we wanted to achieve. In some problems, we know the state in advance. In some problems, we don't know it, and we let the algorithm evolve with the passage of time. And after certain iterations, when we see the fitness reaches and the best value, we stop. Okay, so this is the cycle of the genetic algorithm. So after evaluation, we replace individuals, we discard some individuals from the population, and we replace evaluated children in the population. And once again, we repeat the same steps, 1, 2, 3, 4. Once again, with the new population, we start and we do these steps. Okay, so this is the overall theme, the steps of the genetic algorithm. It consists of 4 steps, very easy algorithm. It consists of 4 basic steps, and this is how it proceeds. So I have constructed a small problem. Let's say we have an image over here, and another image over here. So the problem is, let's say this image is a 3x3 image. It represents our start state. So let's say this is a black image, so all the pixel values are 0. If we want our agent to move from this black state to a white state in which all the pixel values are 1. Okay, so those of you who have this image processing background, they know that zeros are for black and ones are for white. Okay, if the intensities are averaged between 0 and 1, but doesn't matter. Okay, the image processing background is not important. The important thing is that you know that this is the start state and this is the goal state. I mean, if you know that in a search problem we have states, we have state formulation, we have state, so we transition from one state to another state. So the important thing in genetic algorithm is to encode your state, your start state, to encode. This is one of the important steps in genetic algorithm, to be able to encode your start state into a chromosome representation. So here, since the problem is very simple, is very naive, so we just transform this two-dimensional array into a chromosome like this. Okay, so why we have encoded into a 1D vector? Because generally the natural chromosomes, they are in 1 dimensions. Okay, they are strings of 4 bases. Okay, so chromosomes are binary strings. They are strings. So in genetic algorithm representations, we use binary strings like this. Okay, so here we did not use any trick. Okay, so we just transform a 2-dimensional state to a 1-dimensional representation, which is a chromosome. Okay, and we can also, I mean, if you want to transform the goal state into a chromosomes, it will be an array like this, but all the values are going to be 1. Okay, so one important thing is to transform your state into a chromosome, and the other thing is to define a fitness function for your problem. Okay, so in this problem, our start state is a 2-dimensional arrays of 0. So the start state is a bad state. Okay, we don't want this state. We want a state with all the values 1. So fitness of the state can be defined, for example, what we want to achieve. Okay, so in this case, we want to achieve all the values changed to 1s. So fitness function can be defined the number of 1s in the chromosome. Okay, so in the chromosome, in a bad state, we have all the values set to 0, but we want a chromosome with all the values set to 1. Okay, so this is the fitness function of our algorithm. Okay, so according to this function, if we check the fitness of our start chromosome, so this chromosome, the fitness of start is 0. You just count the number of 1s in the chromosome. There are no 1s, the fitness is 0. Likewise, you can compute the fitness of the goal chromosome as well. So the fitness of the goal chromosome will be 9. Okay, but this is something that we want to achieve. Okay, now if you understood the problem is going from this start state to this goal state. Okay, so for the time being, let's be naive and let's solve this simple problem using genetic algorithm. So how we are going to solve this problem using genetic algorithm? Remember that in the genetic algorithm, the first step was to construct the population. Okay, so we are once again start with some initial population. So the first step is to construct an initial population. So how we construct an initial population? Here I have set the size of the initial population to 4. Okay, but usually, I mean, what should be the size of the initial population? There is no hard and fast rule for this. The size of the population can be any number. Okay, but if the number is too high, then first of all, your algorithm is going to take a lot of resources. So for example, if you have the resources, the computational resources, then maybe if your population size is too high, the number is too high, then it's going to be just a random search instead of a search that optimizes with the passage of time. Okay, so it is you can read a lot of papers if you search about the population. So the recommendation by researchers is that the size should be between 30 and 100. It's a good size. Okay, so you can take a population of size from 30 to 100. Here in our problem, we take a population of size 4. Okay, just this is a simple example, so I want to explain stuff to you. So I take a population size of 4. Okay, so how I constructed, so remember the problem. So we had a state, and we knew how we constructed a representation for our chromosomes. So we can represent this state in the form of the chromosomes like this. Now we generate random parents in the population. Okay, so random parent means just by flipping one of the bit we generate random parents. So I have generated 4 random parents. Okay, remember in our problems, in real problems, we are again going to construct these populations by generating parents randomly. So first parent is constructed by taking the state as it is. Second parent is constructed by flipping the second and the 6th bit. Third is generated by flipping the 8th bit. Okay, again fourth is by flipping 3 bits in the chromosome. Okay, so once we have generated our population, so in this case a population of size 4, we need to compute the fitness of the chromosomes in the population. Okay, so in constructing population, we need to compute fitness. Remember that the fitness will be computed according to the fitness function. So the fitness function is the number of ones in the chromosomes. So very simple, very easy. Just compute the number of ones in the chromosome. So in our population, parent 1 has 0 ones, so the fitness of P1 is 0. The fitness of P2 is 2 because just there are 2 ones in the chromosomes. Fitness of P3 is 1 because there is just 1. And fitness of P4 is 3 because there are just 3 ones in this chromosome. So this is our populations of individual. Okay. Now the genetic algorithm is inspired, as I said earlier, is inspired from natural evolution. Okay. So like natural evolution, we select parents. We select parents for mating. Okay. So how we are going to select? We are going to select them randomly. Okay. But that randomness will depend on the fitness of the chromosomes. Okay, that randomness will depend on the fitness value of the chromosomes. So in the next step, we are going to select parents. Okay, so like biologically, the living beings are selected for mating. Okay, and it is based on the fitness value. So likewise, we are going to, in the step number 2, we are going to select parents. Okay, so how we are going to select? We are going to select based on the fitness value. So the selection probability of the parent I will be equal to the fitness value of parent I. So if you look at the formula, it's the fitness value of parent I divided by the total fitness of the population. Okay, so what is the total fitness of the population? If we compute, so the population was of size 4, the total fitness is 3 plus 1, 4 plus 2, 6. And the total fitness is 6, and we can compute, we know the fitness of the parent. Okay, so if we compute the selection probability of the individuals in our population, the selection probability of P1 is 0 because the fitness was 0 and total fitness is 6. 0 by 6 is 0. Selection probability of parent 2 is 2 by 6. The fitness of P2 divided by total fitness. Likewise, selection probability of P3 is 1 by 6. Selection probability of P4 is 3 by 6. Okay. So in this step we compute the probabilities, and based on these probabilities we are going to select individuals for the next step, which is recombination. Okay, I'm sure you know how we compute this. We compute we select based on these probability, how we select the individuals. I'm sure you know that if the probability is 0, we are never going to select P1, okay, because it's a parent with bad fitness. Okay, so if the probability of 1 by 6, you know how we can select this parent. Okay, we need an event with 6 outcomes. So if we fix one outcome for P3, if that outcomes comes, we select P3. Okay, this is how we are going to select. So we are going to select parents. So in this step, the selection will be based on these probability values. So which parent will have the highest probability of selection? Of course, P4. The selection probability is 1 by 2 or 0.5. So 50% of the time we are going to select P4, okay, because its fitness value is higher. So from our population, the highly fit individuals will have high probability of selection, and the least fit individuals will have least probability of selection. Okay, but still they are going to have some probability of selection. Okay, so this is the selection step. The third step is to modify the randomly selected parents to generate the offsprings. Okay, so let's suppose that the randomly selected parents are, so first parent randomly selected is P2, and the second parent which is randomly selected is P3. Okay, so P2 is represented here, the chromosome, and P3 is represented here. The chromosome length is from 1 to 9. So in order to modify the chromosome, the first operator that we utilize is called crossover. Okay, so there are different types of crossover. So the first type is, one type is single point crossover. So single point means that we are going to slice the chromosome at one point in the chromosome length. Okay, then there are multi-point crossover, there is uniform crossover, or there is arithmetic crossover. So since we are doing a simple example, so we will only consider the single point crossover. Okay, so how we apply this single point crossover? We generate a random number from 1 to the length of the chromosome. So the length is, you can see the 9 is the length of the chromosome. So we are going to generate a random number between 1 and 9. Let's suppose that the random number generated is 3. So 3 is the randomly generated number. So for single point crossover, we are going to slice the chromosome at this length. So you can see I have divided both parents P2 and P3 between two portions at 0.3. Okay, so P2 is divided into green segment and cyan segment. Okay, likewise P3 is divided into purple and yellow portions. Okay, so you can see you can look at the, if you look at the colors, we can see the crossover is we can generate children by combining the first part of P2 with the second part of P3. Okay, see, 1 is a child, we generated this child by combining first portion of P2 with the second portion of P3. Likewise, we generate C2 by combining the first portion of P3 with the second portion of P2. Okay, so likewise we generate two children from these two parents. Okay, so this is the crossover operation. We did it for P2 and P3. So since we are using generational genetic algorithms, so in generational algorithms we need to create the number of children equivalent to the population size. Okay, so we need to create two more children. Okay, so first we randomly draw P2 and P3. Now we are once again randomly going to draw two more parents. Okay, so let's say the next two parents, randomly drawn two parents, are P4 and once again P3. Okay, since the process is random, so P3 is selected again, for example. So once again we do the same step for single point crossover. We are going to generate a random number between 1 and the length of the chromosome. Okay, so let's say this time the random number generated is 4. So we are going to do once again the same. We are going to divide our chromosomes at this length. Okay, so we are going to divide our chromosome into two portions at 0.4. So you can see P4 is divided into two portions and P3 is also divided into two portions. So once again we are going to do the same. The first portion of P4 will be combined with the second portion of P3 and we make a child C3. Okay, you can see that it consists of the first portion of P4 and the second portion of P3. Likewise, we create another child by combining the first portion of P3 with the second portion of P4. Okay, so these are the two new children. Okay, so after this crossover, so this is the first modification that we do on our chromosomes, okay, to generate the new chromosomes. Okay, after the crossover modification, we will have 4 children. So like this. Okay, so it's after the single point crossover, we have modified our chromosomes and generated the offsprings, 4 offsprings like this. Now the one thing before I talk about the next modification, why we apply this crossover. I mean, what is the importance of this crossover? Crossover is a genetic operator which is applied in natural evolution. Okay, so genetic material is combined using this operator. Okay, so why we use it in our algorithm? What is the importance of this? Crossover is called, it's important, it's called a convergence operator. Okay, what does it mean by convergence? Convergence means if you are somewhere in the state space, the crossover is going to allow you local movement towards the maxima. Okay, so if you are at a hill of global maxima, the crossover is going to this operator is going to take you towards states that go towards global maxima. Okay, so this is a convergence operator. It will converge your solution. Okay, if you don't do crossover, your algorithm will not converge. Okay, the next step is mutation. So next modification is mutation. So the 4 children that we modified using crossovers are C1, C2, C3, C4. Now we are going to apply mutation on these 4 chromosomes. So how do we apply mutation? Very simple. The mutation is applied by using a probability. Usually it's a very small probability. So for example, 0.01 or 0.001. Okay. So how we apply it? At each bit of the chromosome, we are going to calculate this probability, okay, through a process. So let's say we are going to generate a random number between 1 and 100, and we are going to fix one number, and if that number comes, then we are going to modify this bit, otherwise we are not going to modify this. So we are going to apply this at each bit of the chromosome. Okay, so with this probability, and you can see the probability is 0.01. So 1 out of 100 times you are going to modify the bits. Okay, so we apply on each bit, generate a random number from 1 to 100 and fix the number. If that number comes, you modify the bit. Okay, mutation is just mutating. If there is 0, you make it 1. If it is 1, you make it 0, and so on. Okay, so here I have applied this mutation on these 4 chromosomes. So you can see in C1 the 5th bit is changed, in C2 none of the bit is changed, in C3 the 7th bit is changed, and in C4 2nd bit is changed. Okay, so after mutation your chromosomes or the offspring that you have generated will be modified in this fashion. Okay, so now the question is why we apply mutation on our children. And once again, this is derived from natural evolution process. So in biology there are random mutations. So from the artificial intelligence problems, in AI problems, why we apply this mutation operator? Because this allows you to move in your large state space. Okay, so this mutation is also called the exploration operator. Okay, so if you are somewhere in your state space, by mutating your chromosome, a bit of your chromosome randomly, you move to another portion of the state space. Okay, so consider a huge state space in which you have a lot of states. Mutation is an exploration. It allows you to explore different portions of the state space. Okay, so what is going to happen if this mutation rate is let's say is very high? So instead of 0.01, the mutation is, let's say, 0.995, or I don't know, but some high number. So if the mutation is high, we are going to do a lot of exploration of the state space. That means instead of going towards the optimum value, we are just going to do a random walk in the state space. Okay, likewise, what is going to happen if this mutation rate is too low? For example, instead of 0.01, it is 0.000000001. Okay, so or I don't know, but a very small number. So what is going to happen if the mutation is too low? Okay, so if the mutation rate is too low, the exploration will stop. Okay, or will happen with the very low frequency. Okay, so the algorithm is not going to find the global optimum, or it will take a lot of time. Okay, so this is why mutation is applied. Okay, so after mutation we will have parents like this, children like this. Okay, so after mutation operator is applied, the next step is to evaluate the newly generated offsprings. Okay, in evaluation, again an important step of genetic algorithm, we are going to evaluate the newly generated children. Okay, so we compute their fitness value. Okay, now in some problems we know that what is the optimum. For example, the problem that we were doing, we know that the goal state is this state. Okay, we know in advance that this is something that we want to achieve. If by chance we are able to achieve this goal state in the offsprings, then we are going to stop the algorithm. Okay, we are going to evaluate, calculate, compute the fitness value. We know the maximum we need is 9. If we achieve 9, we are going to stop the algorithm. Otherwise, if we have not achieved the required fitness value, then we are going to move to step 1 once again. So repeat from step 1 to 4. So we are going to replace the modified children to the parents in the population. Okay, so replace these children with the population and start the process again. So again we do the selection, we do the modification, crossover, mutation, and once again evaluation. Okay, so we repeat these steps once again. Okay, so in some problems we don't know what should be this stopping condition. Okay, so we don't know maybe the maximum fitness value, for example. So in that case we run our algorithm for quite a bit of time, and after some time the solution is going to converge towards the global maxima. Okay, and we can check the fitness value, okay, with the passage of time and store it and ultimately return that state. This was all about the steps of the genetic algorithm. Now we are going to talk about the applications of genetic algorithm, the key application where it is applied. Okay, those applications are not just limited to the one are listed. I only listed the applications which are very famous. Okay, otherwise there are myriad of applications apart from these areas. Okay, so it's a very powerful algorithm. It is extensively used in a number of applications. For example, the very famous application is feature selection. Okay, so we use genetic algorithm to select the optimum number of features that give you the best performance for a classifier. Likewise, it is also used for optimizing engineering designs and to boost the cycle and to speed up the design process and to achieve the optimum values of a design. We apply once again genetic algorithm. Okay, so likewise another application is for scheduling, for traffic and shipment routing and maybe scheduling, and we efficiently adopted by many sales-based companies. It is time-saving and economical. Likewise, there are applications in robotics. Think of using GIS to make robots that learn human-like behavior. Okay, so you want to optimize the robot's behavior to make it close to human behavior. Okay, so once again you can use genetic algorithms to optimize robots behavior. Okay, so this is very powerful algorithm and it has a lot of different applications. Thank you very much for listening.